Okay, so let's try doing some problems involving free damped harmonic oscillators, just to try to come to grips a little bit with all of these um, new ideas. Yeah, so that's under damped. Oh, and I was able to paste finally. I think I'm learning. Okay, but let's do the problem. I'm gonna just rip these from the textbook. This is from section 2.4 in the textbook. But here we go. Let's do the following problem. A mass of m kilograms is on a spring with spring constant K equal to 3 newtons per meter. Okay, and we're going to assume that there's damping, and the damping constant is C, and that's going to be equal to 2 Newton. Oh gosh, I can write Newton seconds per meter. All right. You can check that the units on C should be Newton seconds per meter, which makes sense. If C is multiplying by velocity and we get a force, then yeah, you should be able to see that more or less easily. Find the mass m naught for which there is critical damping. And then once we find m naught, okay, the question becomes there's another question. If m is less than m naught, does the system oscillate or not? That is the system overdamped or underdamped? Underdamped or overdamped? Is the system more like a dash pot, as in the overdamped case, or more like a pendulum, which actually does oscillate? Um, let's check it out. So, this is completely determined, of course, by what we've been calling the discriminant, p squared minus omega naught squared. Okay, but I can't remember what I mean. I can, but I don't really like. Let's say I don't remember what p and omega naught are. I do remember how we derived the original sort of a differential equation for the harmonic oscillator. Remember that was mx double prime plus oh god, I claim I do. Yeah, cx prime plus kx equals 0. This is my free damped harmonic oscillator. And what I know is that the characteristic polynomial for this is mr squared plus cr plus k. And so the discriminant, which is the quantity which determines whether we are underdamped, overdamped, or critically damped, is given by, in this case, c squared. It's the coefficient in front of the r term squared, so that's c squared minus 4 times m times k. And I claim, and I'm right, that this discriminant is more or less equivalent to what we would obtain if we used p and omega naught and all that. Okay, but in particular, we can use this formula because we are given the value of k and the value of c. So we can then fill in the blanks here. C in this case is 2. C is 2, so we get 4 minus 4. M is what we're hunting for, and K is 3 times 3. So we get 4 minus 12M. Now, what do we want out of the discriminant if we're going to achieve critical damping? So critical damping, the system is critically damped if this discriminant is 0. In other words, if 4 minus 12m is equal to 0. So we want to solve this equation. And it's not that hard to see that m is going to be 1/3 kilograms, right? This implies that the mass which makes this happen is going to be 1/3 of a kilogram. So if the mass at the end of our spring is exactly 1/3 of a kilogram, then we are critically damped. Okay. Now, I think are also now in a position to understand what happens if if the mass is in fact smaller than this value, right? C hasn't changed. K hasn't changed. So if we have an M, which is smaller than 1/3 K, kilograms rather, 1/3 kilograms, what happens to this discriminant? Does it become positive or does it become negative if M is smaller than 1/3 kilograms? Well, if M is smaller than 1/3 kilograms, this quantity right here gets smaller. So rather than this thing being 0, right, it's going to be positive because we're taking c squared minus something smaller now, right? So it's going to be positive. So if M is less than M naught, as we are assuming here, then in fact the system is overdamped. Then, in fact, c squared minus 4mk is positive, and so the system is overdamped. Overdamped and will not oscillate in particular. Good. Okay, so that's how we solve this problem. Okay. Good, good, good. Okay, let's do one more, and then we'll call it. This one will be a little bit trickier, I believe. So a mass of 2 kilograms is on a spring with spring constant K. Oh, no. I don't want to do this one. I want to do this one. Sorry. Let me change it up. So we have a mass. Okay. Let me do this differently. Sorry. I want to do this one. Sorry. Suppose you wish to measure the friction of that a mass of 0.1 kilograms, so 1/10 of a kilogram, experiences as it slides along the floor. Okay, so when we say we want to measure the friction, what we're really saying is what is the damping constant C? So really we're asking, we want to know C. Okay. You have a spring with spring constant 5 newtons per meter. A spring with spring constant, also say K, equals 5 newtons per meter. All right. You take the spring, attach the mass, and affix it to the wall. The spring, the mass to the spring, and the spring to the wall. Okay. You pull on the spring, let it go. And you observe that the mass oscillates with a frequency of 1 hertz. So it goes through one, remember, cycle every second. That's what that means. What's the friction? What is C? That's the question. This problem is interesting because it gives you a way of empirically determining the friction, right? That's what's interesting, I suppose, about it. Okay, so how do we go about doing this? Well, what we are seeing here with this oscillation of 1 hertz, this means that our what we have in our system here is a underdamped harmonic oscillator. An underdamped harmonic oscillator. So we're in this case here that we talked about in the last video. Okay? And what we are told, the data that we are given, is about the frequency of the oscillation. Okay? We are told something, in other words, about omega 1. And critically, we're told something about omega 1, not omega naught, okay? Because omega naught is not the same thing as the way that this damped harmonic oscillator oscillates. Omega naught is what's called the natural frequency, which is what the mass spring object would do, mass spring system would do in the presence of no damping, okay? So we're told omega 1. Omega 1 is 1 hertz. Okay, cool. But we're more accustomed to thinking about omega 1 in terms of units of radians per second. So right now we have omega 1 being equal to 1 hertz. And just as a reminder, 1 hertz is 1 cycle per second. That's what a hertz is. It's a cycle. So like 10 hertz is 10 cycles per second. All right. What is a cycle? A cycle is 2 pi radians. So this thing is just equal to 2 pi radians per second. All right. And that's going to be important because that's a more natural value for omega 1. All right. That fits with the sort of setup that we had when we were talking about this entire theory. Yeah. Okay, so that's omega 1. It's 2 pi radians per second. What is it that we're hunting for here? We are hunting for C. Okay. Now we know that from this green formula right here, and maybe I'll just to prove it to you, I'll take this and I'll duplicate it and bring it down here. Oh, shoot. I have to bring it all the way down here. Here we go. There's our omega 1. On the other hand, we know that omega 1 is equal to omega naught squared minus p squared. What's omega naught again? Oh, right. Omega naught is square root of k over m. And what was p again? P is equal to, oh, shoot. I could just look at my notes, right? This is the value of having notes. C over 2m. So I go back down here. This is C over 2m. And what is it I'm hunting for again? Don't forget, I'm hunting for friction. So now I can plug this stuff in because I know omega 1 is 2 pi. So maybe I'll do this in red. So 2 pi radians per second is equal to the square root of omega naught squared. That's the square root of k over m. So that's squared, which is k over m. I'll fill in the blanks on what k and m and all that are. Minus, now, p squared. So P squared is C squared over 4M squared. Does that make sense? Okay. Now I can square both sides. Oh, okay. Let me fill in the blanks, actually. Because what's K? That's given to me in the problem, isn't it? K is 5 newtons per meter. And what's M? M is 0.1. Okay, there we go. And then we subtract C squared, the thing I'm hunting for, divided by 4 times 0.1 squared. I'm not scared, are you? Maybe. Okay, let's square both sides now. So here I get 4 pi squared is equal to, now what's 5 over 0.1? How many 0.1s go into 5? If I have $5, how many dimes is that? Oh gosh, you children don't have a lot of experience with coins. You have 50 dimes. 50 dimes is $5. And then C squared is what we're hunting for. And then 0.1 squared, 1/10 squared is 1/100th, right? And then we have 4 over 1/100th. So that's 4 over 100. 4 times 1/100th. This is a mess. But that's 1/25th. So this equation ends up being 4 pi squared equals 50 minus 25 C squared, I believe. And then what am I trying to do? Oh, I'm trying to solve for C squared. Or C, rather. So I subtract 50. And then I divide by negative 25. And then I'm going to rewrite it a different way, because negative 50 divided by negative 25 is 2. And then I have 4 pi squared over 25. This is C squared, so C is going to be the square root of this. Yeah. And what are the unit? Sorry, I don't like the way I wrote that square root. And I don't like I write the negative sign. It looks messy. Okay. And what are the units on this C? Well, they are newtons seconds per meter. Newtons seconds per meter. And that's it. And I don't know what that number is. I'm confident, I'll say, that it's not a complex number. I think it's a real number. 4 pi squared, I mean, pi is like roughly 9, or 3. So pi squared is like roughly, it's like a little bit more than 3. So pi squared maybe is like 10, and 4 times 10 is 40, and 40 divided by 25 is, it's 1 point something. So 2 minus that is, again, a positive number, and that's going to be our C. But this is interesting because it gives us a way of empirically determining the value of the friction, like what C is, which, maybe we wouldn't have had previously. Okay, cool. Hopefully that was interesting and enlightening. In the not so distant future, what we're going to do is think about what happens when we're no longer free, when we actually have an external force acting on things. And this is where things get real spicy. Okay. But that'll be for the future, not for now. Okay. So long.